What if the Big Bang, the universe's most trusted origin story, just snapped under the weight of its own evidence? The James Webb Space Telescope wasn't built to chase wild theories. It was designed to confirm what generations of Nobel-winning scientists declared as fact: a 13.8 billion-year-old cosmos, expanding since day one, written in microwave echoes and red-shifted galaxies. But Webb's first data shattered every expectation, revealing sprawling, fully formed galaxies in an era where nothing that complex should exist. If these new discoveries break the rules that built modern cosmology, what happens to everything we thought we knew about reality itself? The answers start with a single question: what if our cosmic origin story just got rewritten? In 1929, Edwin Hubble published a discovery that would upend humanity's sense of the cosmos. By measuring the light of distant galaxies, Hubble noticed a peculiar pattern. The farther away a galaxy appeared, the redder its light became. This redshift, a stretching of light to longer wavelengths, suggested that these galaxies were racing away from us. The universe, it seemed, was not static or eternal, but expanding in every direction. Hubble's observations, made at the Mount Wilson Observatory using the 100-inch Hooker telescope, provided the first clear evidence that the fabric of space itself was stretching. He plotted the distances of dozens of galaxies against their redshifts and found a linear relationship. The farther the galaxy, the faster it receded. This became known as Hubble's law, and it pointed to a universe with a definite beginning, a moment when everything was packed into a single, dense state before space itself began to balloon outward. The implications were profound. If the universe was expanding, then rewinding the clock would lead to a time when all matter and energy were compressed together. This idea, controversial at first, gradually gained traction as more astronomers confirmed Hubble's findings. The expanding universe became the backbone of modern cosmology, replacing the old picture of an unchanging cosmos with one that had a birth, a history, and a possible end. Hubble's work did not stand alone. It fit with earlier theoretical predictions from Albert Einstein and Georges Lemaitre, who had independently proposed that Einstein's equations allowed for an expanding universe. But Hubble's measurements provided the crucial observational anchor. The redshift distance relation, now a fundamental law of astronomy, transformed abstract mathematics into a narrative about the origin and fate of everything. As the evidence mounted, astronomers began searching for other relics of the universe's explosive beginning. The next chapter would come from a faint, all-sky signal, the cosmic microwave background, a whisper of the fireball that once filled all of space. But it was Hubble's chart, drawn nearly a century ago, that first set the universe in motion. In 1965, a faint, uniform glow was detected across the sky, not from any star or galaxy, but as microwave radiation coming from every direction. Arno Penzias and Robert Wilson, working at Bell Labs, had stumbled onto the cosmic microwave background, or CMB. This was not just noise. It was the cooled remnant of the universe's first light, a direct echo of the hot, dense state predicted by Big Bang theory. The CMB's discovery provided a smoking gun for the expanding universe story. It earned Penzias and Wilson the Nobel Prize in Physics in 1978. The CMB wasn't just a relic, it became a precise tool. Its temperature, mapped to 1 part in 100,000, revealed tiny fluctuations, seeds of future galaxies. These ripples matched the statistical fingerprints predicted by theory. Over decades, satellites like COBE, WMAP, and Planck refined the map, confirming that the universe is flat, nearly homogeneous, and filled with dark matter and dark energy in just the right proportions. The precision was staggering. The lambda CDM model, named for Einstein's cosmological constant, lambda, and cold dark matter, emerged as the gold standard. It offered a recipe: 5% ordinary matter, 27% dark matter, 68% dark energy. Every major observation, galaxy clustering, element abundances, supernova distances, fit the model's predictions. But the CMB did more than explain the past. It set the clock for what should happen next. The model predicted that after a long cosmic dark age, the first stars would ignite about 200 to 400 million years after the Big Bang. Galaxies would begin small, chaotic, and faint, gradually merging and growing over hundreds of millions of years. The earliest galaxies, according to Lambda CDM, should be rare, dim, and primitive, barely more than clumps of gas and newborn stars. The theory didn't just explain what had been seen, it forecast what the next generation of telescopes would find. In 2006, John Mather and George Smoot were awarded the Nobel Prize for their work mapping the CMB's subtle patterns. Their data cemented Lambda CDM as not just a story, but a predictive framework. Cosmologists entered the era of precision cosmology, confident that the model would pass every new test. The universe, it seemed, was an open book, one whose next pages were written in the language of Lambda CDM, waiting for the right telescope to read them. Orbiting nearly 1 million miles from Earth, the James Webb Space Telescope operates at the second Lagrange point, a gravitational sweet spot where the pull of Earth and Sun balance perfectly. Here, Webb remains locked in constant shadow, shielded from sunlight by a 5-layer sunshield the size of a tennis court. This barrier, thinner than a human hair in places, cools the telescope's instruments to minus 233 degrees Celsius, cold enough to silence the faintest thermal whispers from the telescope itself. At the heart of Webb's design is its primary mirror, a gleaming mosaic of 18 hexagonal segments coated in gold. Each segment measures 1.32 meters across, and together they form a 6.5 meter wide eye, more than 2.5 times the diameter of Hubble's. This vast surface gathers light that has traveled for over 13 billion years, focusing it with a precision measured in nanometers. Such sensitivity is only possible because the mirror and instruments are kept colder than Pluto's surface, preventing their own heat from drowning out the faint glow of distant galaxies. Webb's 4 main instruments, NIR-CAM, NIR-SPEC, MIRI, and FGS/NIRISS, are designed to capture infrared light, the stretched remnants of starlight emitted when the universe was young. Unlike visible light, which is blocked by dust and gas, infrared slips through cosmic veils, revealing stars and galaxies otherwise hidden from view. The detectors are so sensitive they can register the heat signature of a bumblebee at the distance of the moon. Building Webb required engineering feats never before attempted. The primary mirror, too large for any rocket fairing, was folded like origami for launch, then deployed and aligned in space with microscopic accuracy. Each mirror segment can be adjusted individually, using motors that move in steps smaller than the width of a human hair. The sunshield's 5 layers had to unfurl in sequence, tensioned and separated so that even a tiny tear would not compromise the mission. At every stage, Webb's design choices were driven by a single goal: to see farther and fainter than any telescope before it. Its position at L2, its gold-plated mirror, its cryogenic instruments, each element works in concert to allow Webb to collect the universe's oldest light. The result is a time machine of unparalleled power, capable of capturing the faintest glimmers from the dawn of the cosmos. With these tools, astronomers can trust that what Webb sees is not a trick of the instrument, but a true record of the universe's earliest chapters. Cosmologists entered the Webb era with a clear set of expectations. The telescope was not just a technological marvel, it was built to resolve the universe's first light, to catch the moment when darkness gave way to stars and galaxies. The standard model laid out a timeline. After the Big Bang, the universe cooled, hydrogen formed, and for hundreds of millions of years, nothing but blackness and gas filled the expanding void. Only after 200 to 400 million years, theory said, would the first stars ignite, clustering into small, turbulent galaxies. These would be faint, chaotic, and rare, barely more than knots of gas and newborn suns, still assembling into larger systems. Webb's infrared vision was tuned precisely for this challenge. Light from the earliest galaxies, stretched by cosmic expansion, falls deep into the infrared by the time it reaches us. Webb's gold-plated mirrors and cryogenic detectors were engineered to catch these ancient signals, peering further back than any telescope before it. The mission's main goal was to see galaxies, as they appeared just 400 million years after the beginning. Objects so distant their light had traveled more than 13 billion years. Astronomers expected to find a sparse population of dim, primitive galaxies, each one a snapshot of cosmic adolescence. The scientific community was confident in its predictions. Decades of computer simulations and deep Hubble surveys had mapped out the likely population of early galaxies. These models forecasted that the first galaxies would be small, with stellar masses less than 1 billion times that of the Sun, and forming stars at a measured pace. The brightest galaxies at these epochs were expected to be rare outliers, requiring tens or even hundreds of hours of observation time to detect. Anything more luminous or massive would have required star formation at efficiencies far beyond what physics allowed. Webb's mission was to confirm this sequence and fill in the details, to measure how quickly the first galaxies grew, how efficiently gas turned into stars, and how early cosmic structure emerged from the primordial fog. The hope was that Webb would provide the final, high-resolution proof that the standard cosmological model could not only explain the past, but predict the future. Astronomers anticipated refining the timeline, perhaps finding a few surprises in the details, but not overturning the core story. The expectation was simple. Webb would reveal the dawn of galaxies, just as theory had written it. The universe's expansion rate, known as the Hubble constant, sits at the center of a scientific standoff. Two main methods have been used to measure it, and the results do not agree. The first approach, often called the distance ladder, builds step by step from our own neighborhood outward. Astronomers start by measuring the distances to nearby stars using parallax, the tiny shift in a star's position as the Earth orbits the Sun. Next, they calibrate Cepheid variable stars, which pulse in a way that reveals their true brightness. By comparing their known luminosity to how faint they appear, distances to nearby galaxies can be calculated. Type 1 supernovae, which explode with predictable brightness, then extend the ladder even farther, anchoring the scale out to hundreds of millions of light years. Adam Rees and his colleagues have refined this technique for decades. Their measurements, using both Hubble and now Webb, consistently find a value of about 73 kilometers per second per megaparsec. This means that for every 3.26 million light years you travel, the universe expands another 73 kilometers per second. The numbers are precise, the error bars shrinking with each new observation, yet the answer stands apart from what the early universe seems to reveal. The second method looks much deeper in time. Instead of measuring local galaxies, it analyzes the cosmic microwave background, the afterglow of the Big Bang itself. Satellites like Planck have mapped this faint radiation with exquisite detail. By fitting the temperature fluctuations in the CMB to the equations of the standard cosmological model, scientists predict how fast the universe should be expanding today. This method yields a lower value, around 67 kilometers per second per megaparsec. The numbers are just as precise, but the gap between the two methods has persisted and even widened as measurements have improved. The difference is not small. The local measurements and the early universe predictions disagree by more than can be explained by random error or overlooked dust. The tension stands at about 5 to 6 sigma, well beyond what could be chalked up to chance. Each camp has checked and rechecked its methods. Rees's team, using Webb's infrared vision to cut through cosmic dust, confirmed that the Cepheid measurements hold up. The Planck team, with a completely different approach, finds its numbers equally robust. The stakes are clear. If both sets of measurements are right, something fundamental is missing from our understanding of cosmic history. The universe may hold secrets in its earliest moments, or in the way dark energy has changed over time. For now, the two expansion rates, 73 and 67, stand as rival answers to a question that should only have one. The mismatch is not a technicality. It is a direct challenge to the story that has guided cosmology for a generation. Adam Rees sits at the crossroads of modern cosmology, a Nobel laureate whose work helped prove the universe's expansion is speeding up, not slowing down. In 2011, he shared the Nobel Prize in Physics for uncovering that acceleration, a discovery that forced dark energy into the cosmic equation. But the numbers that once brought clarity now bring unease. For years, Rees has led the charge to measure the Hubble constant using the so-called distance ladder, parallax, Cepheid-C, and supernovae. His team's results, checked and rechecked, consistently point to a universe expanding faster than the early universe data allows. The difference isn't a rounding error, it's a chasm, one that has only grown as measurements have become more precise. The tension between local and early universe expansion rates stands at over 5 sigma, a statistical gulf that no one can ignore. When Webb came online, Rees saw an opportunity. The telescope's infrared vision could pierce cosmic dust and resolve individual Cepheid stars in distant galaxies with a clarity Hubble could never match. If previous measurements were skewed by dust or crowding, Webb would reveal it, but the results held firm. The expansion rate from Cepheids, measured with Webb's sharp eye, matched the numbers from earlier work. The gap with the cosmic microwave background, measured by Planck and other satellites, remained stubbornly wide. For Rees, this isn't just a technical puzzle, it's a personal reckoning. He has staked his reputation on the integrity of these measurements, and now finds himself questioning the very framework he helped build. In interviews, he has grown impatient with suggestions that some overlooked error could explain away the tension. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe, he told colleagues. The words carry the weight of someone who has spent decades trusting the data, only to find the foundations shifting beneath his feet. The community's response has been mixed. Some urge caution, suggesting the answer lies in subtleties yet to be uncovered. Others, like Russ, see the persistence of the tension as a sign that something deeper is at play, perhaps new physics, or a flaw in the standard model itself. The debate is no longer about numbers, but about the story those numbers tell. As Webb continues to deliver sharper, more distant measurements, Rees remains at the center of the storm. The crisis is no longer abstract. It's written in the numbers, in the confidence intervals that refuse to overlap. For a scientist who once helped define the cosmic narrative, the possibility that the universe is telling a different story is both unsettling and electrifying. When the first deep field images from Webb arrived, astronomers expected to find faint smudges, tiny, scattered islands of stars, just beginning to assemble in a dark and turbulent sea. Instead, they saw something no one had predicted: vast, brilliant galaxies, shining with the mass and order of modern giants, but existing only 300 to 500 million years after the Big Bang. Glass Z13, one of the earliest confirmed by Webb, appeared as a compact but intensely luminous system. Its estimated stellar mass approached 1 billion times that of the Sun, comparable to the Milky Way, but at an age when the universe itself was barely out of infancy. Erica Nelson, an astrophysicist at the University of Colorado Boulder, put it bluntly, "It's bananas. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form." The standard model predicted that galaxies at this epoch would be small, chaotic, and rare, mere clumps of gas and a few newborn stars, still struggling against gravity's pull. But Webb's images revealed not just isolated outliers, but a whole population of massive, well-structured galaxies. Some formed stars at rates 10 times higher than expected, their brightness rivaling galaxies billions of years older. The numbers forced a reckoning. In the Lambda CDM framework, assembling a galaxy with 1 billion solar masses of stars in less than 400 million years should be nearly impossible. Gas needs time to cool and collapse, stars need time to ignite, and heavy elements, the building blocks of planets and life, required generations of supernovae to enrich the interstellar medium. Yet Webb found galaxies with complex chemistry and mature populations, hinting at cycles of star birth and death that had already played out in cosmic fast-forward. The mass estimates came from careful modeling of the galaxy's infrared light, using Webb's NIRCam and NIR spec instruments to measure both the brightness and the color of their starlight. The more massive the galaxy, the redder its light appears, as older, cooler stars begin to dominate the glow. For Glass Z13 and its peers, the data pointed to systems that had already converted much of their available gas into stars, far more efficiently and far more quickly than any simulation had allowed. The surprise did not end with stellar mass. Some of these early galaxies showed evidence of dense central bulges, spiral-like structure, and even the telltale X-ray signatures of active black holes millions of times the mass of the Sun. The implication was clear. Not only had these galaxies grown large, they had grown up, reaching a level of organization and maturity that theory reserved for much later epochs. For theorists, the shock was immediate. If galaxies could reach such size and complexity so soon, then either something fundamental was missing from the models, or the physics of the early universe operated under rules no one had anticipated. The discovery of these cosmic skyscrapers in the Stone Age was not a single anomaly to be explained away. It was a direct challenge to the timeline of structure formation, the efficiency of star birth, and the very assumptions that underpinned decades of cosmological theory. Webb's findings left astronomers with new questions. How could so much mass gather so quickly? What processes could accelerate star formation to near-perfect efficiency? And if galaxies this big existed just a few 100 million years after the beginning, what else might lurk even deeper in the cosmic dawn, still waiting for discovery? The James Webb Space Telescope's deepest surveys have revealed more than bright, oversized galaxies. They have uncovered a chemical and gravitational puzzle at the heart of the early universe. Some of the most distant galaxies, like MACS 0647 JD at redshift 12.33, show clear signatures of heavy elements in their spectra. These metals, elements heavier than helium, forged in the hearts of stars, should have taken hundreds of millions of years and several generations of supernovae to build up. Yet the oxygen abundance measured in MACS 0647 JD already reaches about 13% of the Sun's, just 350 million years after the Big Bang. The direct method, relying on the faint O34363 auroral line and supported by the James Webb Space Telescope's MIRI instrument, confirms that this is no artifact or calibration error. The galaxy's light carries the unmistakable chemical fingerprints of a history that should not have had time to unfold. This story repeats across the earliest cosmic dawn. The James Webb Space Telescope has compiled dozens of galaxies at redshifts above 8 with direct metallicity measurements, some showing metallicities as high as a third of solar. Their spectra, captured with NIR spec and MIRI, reveal both the bright nebular lines and the faint, temperature-sensitive auroral lines needed for a robust abundance calculation. The uncertainties, often as low as 0.1 to 0.3 dex, are small enough to rule out measurement error as the main explanation. In some cases, the chemical richness is accompanied by signs of mature dust, another product of stellar evolution, hinting at a cycle of star birth, death, and enrichment already well underway. But the chemical surprise is only half the story. The James Webb Space Telescope's sharp vision has also exposed a population of ancient black holes, far more massive than theory predicted for the early universe. In the galaxy UHZ1 at redshift 10.1, a supermassive black hole weighing around 40 million times the mass of the Sun shines as a powerful X-ray beacon. Its presence was confirmed by Chandra, but the James Webb Space Telescope's data revealed that the black hole's mass rivals, or even exceeds the total stellar mass of its host. This is not an isolated case. CEERS 1019, another galaxy just 570 million years after the Big Bang, hosts a black hole of 9 million solar masses. Across the highest redshifts, black holes between 10 and 50 million solar masses crop up in galaxies that, by all rights, should still be assembling their first stars. These masses are not speculative. The James Webb Space Telescope's NIR SPEC instrument resolves the broad emission lines, H-alpha, H-beta, and others, whose widths encode the velocity of gas swirling near the event horizon. Applying the virial method and calibrating with local active galaxies, astronomers derive black hole masses with uncertainties usually within a factor of 3. Multiple emission lines, sometimes cross-checked with X-ray luminosities, point to the same conclusion. Black holes in the early universe grew fast, sometimes outpacing their entire host galaxies. In UHZ1, the black hole's mass is nearly equal to the stars around it, a ratio that in today's universe is off by a factor of 1,000. The chemistry and the gravity tell a single, disquieting tale. Heavy elements and supermassive black holes appear together far too soon in a universe that should have been too young for either. The little red dots, compact, intensely red galaxies, dot the James Webb Space Telescope's deep fields, each one a record of fast-forwarded cosmic evolution. Their spectra show the fingerprints of multiple generations of stars. Their cores flicker with the light of black holes that have already reached maturity. The standard timeline, with slow chemical enrichment and gradual black hole growth, cannot account for the speed or the scale of what the James Webb Space Telescope observes. The evidence is relentless. Metals where there should be only hydrogen and helium. Black holes that outweigh their hosts. Galaxies that have lived entire lifetimes in the cosmic blink of an eye. The data leaves little room for comfort. If the universe played by the rules set out in the standard model, these objects should not exist. Yet there they are, written in the spectra and the shadows of the earliest light. The need for new processes, or even new physics, now stands at the center of the cosmic story. Adam Rees turned to Webb's sharp vision for a final answer. His team focused on the distance ladder, the stepwise method that starts with parallax, then Cepheid variable stars, then Type 1a supernovae, to measure the universe's expansion rate. The hope was that Webb's infrared clarity would expose any hidden bias, any dust or crowding that might have thrown off earlier measurements. Instead, the numbers refused to budge. Using Webb's NIR cam, Rees's group resolved individual Cepheids and galaxies up to 100 million light-years away, cutting through cosmic fog and confusion. The result? A Hubble constant of about 73 kilometers per second per megaparsec, matching the value from Hubble's data, but now with even smaller uncertainties. The precision was striking. The error bars shrank, but the divide did not. The gap with the early universe prediction, 67 kilometers per second per megaparsec, drawn from Planck's map of the cosmic microwave background, remained. Webb's data confirmed that the tension wasn't an artifact of flawed technique or overlooked dust. The numbers stood, side by side, separated by more than 5 sigma, far beyond the reach of statistical chance. Rees published the new results in 2023. The paper's conclusion was blunt: the crisis is real. Webb, built to test the distance ladder, instead reinforced it. The expansion rate measured from local galaxies cannot be made to fit the early universe's story. For cosmology, it's no longer a matter of error bars or calibration. The crack in the standard model has become a canyon. Theories must now reckon with the stubborn reality written in Webb's data. Ideas once confined to the margins of cosmology are now finding new attention. Some theorists propose that a burst of early dark energy, active only for a brief window after the Big Bang, could have sped up the growth of structure, making it easier for galaxies and black holes to form in record time. Models like these suggest that the universe's expansion history might have included phases we never imagined, with dark energy waxing and waning long before it began its current, steady push. Others look to cyclic cosmology, where the cosmos is not a one-time event, but an endless series of expansions and contractions. Roger Penrose's conformal cyclic cosmology, for example, envisions a universe where each cycle leaves behind subtle fingerprints, patterns in the cosmic microwave background, or perhaps even the seeds of galaxies that appear too soon. In this view, the Big Bang is not a unique beginning, but a bridge between cosmic epochs, each one giving rise to the next. These alternatives are not yet consensus. Each faces its own hurdles, from matching the precision of cosmic background maps to explaining the details of galaxy formation. Yet the mere fact that such models are on the table signals a shift in the field. Researchers are also probing the limits of star formation itself, questioning whether the earliest stars formed in short, intense bursts, or if the physics of gas clouds in the infant universe allowed for efficiencies never seen since. What comes next is not certain. Webb's discoveries have forced cosmologists to ask whether the universe is stranger than the standard model allows, or if our tools for reading its history are still incomplete. The search for answers is wide open. Each new observation is a reminder that the cosmos can still surprise us, and that the next theory may come from directions no one expects. In 2022, the James Webb Space Telescope revealed galaxies as massive as the Milky Way, existing just 300 million years after the Big Bang, billions of years earlier than standard cosmology predicted. Nobel laureate Adam Rees confirmed that JWST's precise measurements of the universe's expansion rate, around 73 kilometers per second per megaparsec, still do not match the value derived from the cosmic microwave background, deepening the so-called Hubble tension. Despite decades of consensus built on Hubble's 1929 redshift discovery and the 1965 detection of the CMB, these new observations show stars, heavy elements, and black holes forming far sooner than models allow. The cause of these early cosmic structures remains unknown, and no single theory, whether early dark energy or cyclic cosmology, has yet resolved the contradictions. As of today, the universe's origin story is again under review. The data are public, the debate is open, and the next chapter in cosmology is being written, not in theory, but in evidence.